Hello again. Anna became ill today, so she couldn't be here, and I've briefly looked through the presentation the last half an hour, so we'll just see how it goes. This title is already presented, so just briefly about, Anna is part of Task Force Salmon Lice, like me, and several others presenting. So just briefly about the Task Force Salmon Lice that started out as a large project funded by the industry, the university, and the Norwegian Research Seafood Research Fund. And now, since 2016, and we have 6 PhD students either finished or in progress. 26 master students have finished their thesis in this project or are finishing now. 2 researchers, that's me and Anna, and 7 supervisors or professors involved. Now we're developing it into a research platform from which we apply other funding. For example, this project we're presenting today, the non-medicinal control of sea lice, which I presented from earlier today as well. So now it's about the freshwater treatments. The main part of this work was performed by a master student, Sondre. He's here. He's now about to finish his thesis, and we're presenting his results today. Okay, background. Medical and chemical treatments were previously mostly used, but the lice became resistant to it, so non-medicinal methods have been developed and in Norway they're by far the most common. Freshwater is one of these. The most common way of performing them is to crowd the fish and pump them into a wellboat where they stay in large rooms filled with water with 0 salinity, and the water is circulated and oxygenated, and many parameters are monitored, and the lice are filtered out. Treatment time 4 to 10 hours, and the delousing effect is good, but rarely 100%. So we were wondering what happens to the lice and the egg strings that survive the treatment. Do they hatch and potentially reinfest within a short time after freshwater delousings? We've seen before today that they do that for mechanical and thermal treatments. Salmon lice cannot tolerate fresh water for prolonged periods. Wild salmonids do enter rivers to get rid of the parasite. So the lice can probably not develop resistance like they did for medical treatments. However, there's a concern in the industry that the tolerance may increase. And this would represent a challenge with regard to lice control in aquaculture, especially in those farms where they use it a lot. Yeah. So the aims for this project was to look at the fate of the egg strings, the potential for spreading and reinfecting shortly after treatment, and look at hatching and development to NORWAY and coprolites. And also look at possible tolerance to low salinities, variations in tolerance through the treatment, and if tolerance could be inheritable. The field work was done in production area 6, just around Trondheim is here. yeah, okay. There was sampled from delousing operations at 3 fish farms from 4 treatments. So 2 pens in one location and then 1 in each of the others. So it's here, 1.1 and 1.2 is the same location and then different locations. We can't say where the location, or yeah, we don't. We just give them numbers. Adult females with egg strings were sampled before treatment. After 2 hours exposure, either these samples taken during the operation was either sampled from the filter or from fishing fish out of the well, but they didn't like the disturbance of the fish in that phase, so mostly it's from the filters. So before treatment, 2 hours, 4 hours, and 6 hours exposure, and afterwards on the way out of the well. The field work was adjusted on the way because it was really hard to find enough lice, especially here. So he also sampled pre-adult and adult lice from 2 hours and 4 hours exposure in 2 of the treatments. So he went that first time and then didn't know that everything was going to die, and then we had to do some adjustments for the later ones. At some sampling points, no females with egg strings were found, but where it was possible, 3 to 15 egg strings or egg string pairs were collected, so from 3 to 15 females. The egg strings were taken into a lab and hatched, and it's like a light version of the incubator I showed in my presentation, because this was done in a lab where we had access to seawater and temperature control, so we could just put that water straight in and out again, so it's no recirculation here. The flow in each incubator is 3.5 to 5.5 milliliters per minute. They were hatched there, and then they were counted and sorted, or sorted and then counted in active and inactive Nauplea, and then they were put back into the incubator and then counted again when they were reaching the copepodite stage. So then we were able to follow the offspring of the individual females to copepodite stage. The egg strings were photographed for estimating the number of eggs, and the Nauplea were counted within 24 hours, and the copepodites counted at day 4. I think we'll go here. Okay, so here we have egg string length. It's all the same, very similar in all locations, and the mean number of eggs per egg string is 329 to 381. So you can get like 700 Nauplea from one pair. Here is the proportion of egg strings hatched, and here we can see that after exposure to fresh water, the hatching success is considerably lower. There is no hatching after 6 hours or in the after samples. Yeah, here you can also see how few samples he got at that stage with egg strings. This is the hatching success, the number of Nauplea relative to the number of eggs in the egg string. So this is for each location here, or each pen, and here it's summarized. So it's quite variable, or the before treatments is good hatching and development below here, and after 2 hours it's lower, and here the median is 0, so a lot of them didn't hatch at all. And after 4 hours it's even lower, and in the summary it's even more clear how this goes. It's really, really bad development after a few hours in the fresh water. Then it's the cupidid survival for the egg strings that did hatch. So here all the non-hatching ones are taken away. So it's a bit of the same trend. It's the before is quite high, 60 to 80, and a lot lower after 2 hours, and are very variable here after 4 hours. So this here it's less clear, this trend change here, but certainly a reduction from the before samples. If we look at the numbers, there's about 200 cupidids per egg string here. After 2 hours is about 80, and after 4 hours it's about 60. Okay, then I'll go back to the other methods slide. So in addition to the hatching success and the egg strings, he did a bioassay for looking at the salinity tolerance for the cupidids. So he used the methods in this paper here by Melanie Andrews and Torian Horsberg. And he used mostly 20 cupidids per replicate, and mostly 2 replicates per location, or per pen. But sometimes it was just not enough material, like in the 2 and 4 hours, it was very low. Very hard to get enough material to work with. He used 10 salinities, the seawater control 32, 27, 23, 20, 17, 14, 11, 8, 5, and 2. They were incubated for 24 hours, and then he evaluated them as affected or unaffected, if they were immobile, they were affected, or if they were very, very erratic. I think he also categorized them as affected. Yeah, not sure what to say here. Yeah, so we wanted to look at heritability. So we also tried to raise the F2 generation to look if there was some heritability in the tolerance. I think I'll just come back to that when the figures are coming, because it was very challenging, because everything just kept dying from the freshwater exposure. Okay. This is the F1 generation. So the results from the copepodid from the treatment. So the egg strings we collected in the field, and then he did a counting of how successful it was, and then he used the copepodids to look at the salinity tolerance. We see there's a large variation between the treatments. also within the same location, which is the blue and the red. They're from the same locality, and there's quite a big variation there. After 2 and 4 hours, it's still a lot of variation and slightly lower tolerance. So if we see if we can find some, so if we look approximately 50%, here is that's maybe around 8, and if we look here, it's around 11. And here it's a bit higher, more like 14. So these have already been through freshwater as an egg in the 2 and 4 hours treatments. And then we also took an F0 generation, so he sampled pre-adults and adults from the fish that he took back and then put on a fish in our lab. Some of them survived. It was very high mortality, but some of them managed to produce eggs, egg strings that we could hatch, and we performed bioassays on the copepodites. And here we see that these have a higher tolerance. Here, if you look at the 50 as a guideline, it's between 8 and 5. So it's quite similar to the before samples at the same location. So the same location, this is 3.1, and this is the yellow one here, just the highest tolerance one. So there were large difference between the bioassays where the egg strings had and had not experienced freshwater exposure. Okay. I think I just have to get it all out here so I see what I'm going to talk about. So we wanted to look at the heritability. The plan was to use copepodites from all the different sampling points to infest fish in the lab, and to use those to see if those whose parents had survived exposure were more tolerant. And so the first obstacle was that we only had lice from before the treatment and 2 and 4 hours. Everything later than that just died. The lice from 2 and 4 hours exposure, both the egg strings we collected and the egg strings produced in the lab from adults and pre-adults that were collected in the field after exposure and then put on the fish in our lab, and then they produced completely new egg strings. And we hatched them to copepodites, and they were still not able to infest the fish. So we only have this second generation tolerance assay, bioassay from the before samples, and they're very similar to the F1 before samples at the same location. Okay, so information from the previous graphs were used to calculate EC50, 75, 90, and 95. EC50 is the salinity where 50% of the group investigated was affected, and 75 here, 90, and so on. There were differences in the treatments. Should I skip to the end, or? Huh? Yeah, okay, I'll just skip this and go to the conclusions. So the hatching and development, the proportion of egg strings that hatched was high for before samples and decreased with increasing exposure time. For 6-hour treatment time and more, there was no hatching. The development to Norway and Copepotites showed decreasing success with increasing exposure time, and there were large variation between the treatments. The tolerance to low salinities was harder to work with. The Copepotites from egg strings that had been treated had lower tolerance, or approximately the same, 2 and 4 hours after treatment compared to before. Copepotites with egg strings that had not been treated had slightly higher tolerance, but it's really hard to conclude. And the F1 generation, where the F0 generation had been treated or did not manage to successfully invest the salmon. I think it's really interesting that they were that even the Copepotites from the egg strings produced in the lab were unable to infest. And yeah, that's not so. So our conclusion here is that there's probably no immediate infestation of normal freshwater treatments. Okay, I think I'll just leave there.
Run through it.
Okay. There were large variations in the results. It was tedious and laborious work. It was difficult to get material and few replicates. And I think we need alternative methods to study possible heritability of freshwater tolerance. Thanks.